This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 2, Entropy and the Second Law of Thermodynamics. So we introduced what the second law of thermodynamics was in Section 1. This is going to give you a better explanation of it. So you are going to understand or be able to discuss entropy and thermodynamic state function. That's important to determine whether a process is spontaneous. So you're going to be able to state the second law of thermodynamics, which tells us that in any spontaneous process, the entropy of the universe, system, and the surroundings increases. So you should have looked through the website on entropy explained with sheep. I actually thought it was kind of cute, funny, gave you good information about entropy and how he related it to the sheep and the probability of where those sheeps are going to be. So hopefully you read through that and took some notes. So pause the video, fill in the blanks, and then play to hear my words. So you now know that entropy is just the symbol of S, and it means the measure of randomness or the measure of disorder. I'm always referring to it as disorder, and remember that Mr. Anderson refers to it as dispersal. So either way you want to look at it, the biggest thing you want to know is that more disorder in a system, the more or the larger the entropy is. And you want to know that nature tends to go towards disorder. So again, the universe delta S is always increasing, always in the positive sense. So, and it's determined in terms of probability and how the arrangement of those molecules are. What's the randomness or how probable different arrangements of those atoms are. So if we look at something like this, if water molecules are dropped into a container, they would not be expected to land in the just right places to give a high ordered solid, right? We're talking about water. We're not talking about ice. We're talking about H2O as a liquid. So if the way they land is determined by pure chance, the disordered liquid is more likely to occur. So you know that when you put water into a glass on the molecular level, water molecules are going to be kind of flowing in a disordered pattern all over the place. That has a higher probability of being like this versus water right away getting into this ordered fashion almost as if it was a solid. How about tossing bricks into the air? So if we have a guy in the middle and he's going to toss bricks to the left and he's going to toss some bricks to the right, which one is the way it's going to most probably going to happen? Well, I don't know about you, but bricks are not going to lay nicely like this, right? This is probably not going to happen on the left. It's probably going to just make a big pile of mush, right? Just a big disorderly arrangement. So again, this is entropy. Entropy says that nature goes towards disorder. That's going to happen spontaneously. So what is this law of disorder? It's the natural tendency for these systems to move in a direction where the disorder is maximum or the randomness is maximum. So let's look how entropy increases. I believe you have some boxes that you can write or draw whatever you want. So the first one is states of matter. And we've talked about this before. As you go from a solid to a liquid to a gas, you're increasing in entropy. And if you read or pause the video and read that information, it will explain a little bit in more detail. The next one is, why does gases have greatest entropy? Again, read this over. The biggest thing is the most probable. They have more positions possible. And we'll get into more detail about that. But that's basically why that sheep. If you, again, watched over or looked over, read over that information on entropy explained with sheep, it kind of gets you to understand that the more possible positions molecules have, the more randomness they have, the more disorder they have, the more entropy they have. So how about dividing parts? Again, we talked about stoichiometry in that intro video. If you have one part, like one NaCl molecule, and it's going to break up into two ions, the Na plus and the chloride, Cl minus, you're going to have more parts. So the more parts you have, the more entropy you have. Again, pause the video and make sure to read over that information. Number of moles is the same thing. Entropy tends to increase, similar to what we just said before, 2 moles to 3 moles. So to me, these are kind of the same thing. If we go back to dividing parts and number of moles, they're very similar. When it's just talking about increasing number of moles, you're increasing the number of parts, you're increasing entropy, you're increasing in disorder. And temperature, again, as you increase the temperature, going from cold to warm to hot, what's happening to those molecules? They are moving faster. If they're moving faster, there's more chance of disorder, so it's increasing in entropy. So again, make sure to pause, fill in something, whether you're drawing or writing, make sure you're understanding that information. So more disorder, more entropy, and it's a positive delta S. So again, we've talked about forcing order, like I mentioned, your room, right? You can just put clothes all over the floor, or can you orderly put them in your drawer and in your closet? So we have to force order, but that takes energy. So think about ice melting to water, right? If you have these nice structured, orderly ice crystals, right, and going into water where the molecules are now free to move around, that's going to be spontaneous, right? So the more, the water is more randomly distributed, so therefore water is more disordered, and it's going to have higher entropy, right? So again, naturally, ice to water is going to be a spontaneous process, but we have to force the water to turn into ice. That's why we have a freezer. So entropy change, again, final minus initial, it's the delta. That's why it's a state function, because it doesn't matter the path. We just need to know that final number. We need to know the initial number. And then we can say, okay, overall, if the delta S is positive, increase in disorder, increase in entropy, and we're going to have a spontaneous process. But if it is negative, it's going to decrease in order. And again, these are state functions because it's just final minus initial. And I want to remind you that I keep using this word spontaneous, but in the future, when we talk about free energy, that's really when we're going to know if the system or the process really occurs truly on its own. This is just helping us understand the disorder. Is it increasing or increasing or decreasing in disorder? And of course, if it's increasing in disorder, that means nature wants to do that more often. Again, give it some thought. Think about the equation, and then think of if you can come up with an answer. Read over that, and hopefully that makes sense. So these are some practice problems. So again, going from liquid H2O to gas H2O, is that going to have a positive delta S or a negative delta S? Pause the video, see if you can do all three, and then play to get the answers. If you did not get these answers, please come either talk to me in class or some of your classmates, and hopefully you're getting an understanding of why number 1 was positive, 2 and 3 were negative, and why that is. So the second law of thermodynamics is really, again, nature tends to move towards disorder. Okay, so entropy of a universe increases in any change. And we want to remember that we're not only talking about reactions, but we're also talking about just the processes. And I thought this was neat because this was one of the equations, this second law of thermodynamics, out of the 17 equations that have changed the world. I thought that was pretty neat. And you might want to read over this. Again, it's a more detailed explanation as to what's going on in a second law of thermodynamics coming from that website. And I thought that was pretty neat. So, again, delta S of the universe takes into account the system and the surroundings. So if it's positive, entropy increases, spontaneous reaction or spontaneous process, because that's what nature tends to do. If it's negative, it won't be spontaneous. But now remember, if it's not spontaneous in one direction, it will be spontaneous in the reverse direction. And we want to remember that a 0 delta S means that our system is at equilibrium. Okay, that means that it is a reversible process, right? Equilibrium means that a reaction can go in one direction and it goes in the opposite direction easily on its own, right? So that's why when delta S is 0 at equilibrium, because the reaction can go in either direction on its own. So in other words, if we have a reversible process, delta S of the universe equals these two added up. So what is going to be the overall or the value, positive, negative, or 0, delta S of the universe? Hopefully you got 0, just like what we talked about. And in an irreversible process, again, our delta S of the universe is going to be greater than 0. Okay, so it's going to be in the positive sense because it's going to happen in the forward direction. It's going to be spontaneous that way, but it's not going to go back. So give it some thought. Hopefully you came up with something along those lines in your head. Okay, see you in class.